All right, so today we're going to talk about problems that involve friction. So specifically what we're going to do is talk about problems solving them using friction. And an example of that would be, if you have a box and you're dragging it on the ground with maybe some tension force. In the past we've said, okay, there's a frictional force that was equal to 10 newtons. And now we're going to figure out how do we actually calculate that value of 10 newtons. Where does that value come from? So when we calculate friction, if you think about it, you have a box sitting on the ground and you have some applied force, but you can't get the box to move. Well, why? Because there's friction holding it back. And we know if the box is pretty heavy, it has a lot of gravitational force. Well, it's balanced, so there's going to be a lot of normal force. And if it's heavy, it's hard to push. So that friction force is going to depend on the normal force, not the gravitational force on the object, but actually the normal force of the object. The other thing that it's going to depend on when we look at this, if we zoom in to the bottom of the box here, you're going to see that the floor has tiny little bumps and the box has tiny little bumps. And those bumps are called micro welds, and they get stuck together. And that's what gives us this friction then, is those micro welds. And we measure that by this value called mu. And this is the Greek letter mu. And I think they call it a mu because it's not really sure if it's an M or a U. Or you can think of the Pokemon character Mew. So that little guy there is the Greek letter mu. So what is mu? Mu is the coefficient of friction. So mu is the coefficient of friction. And what does that mean? Well, it shows the percentage of N that shows up as friction. So the idea with that is that the values of mu are going to be between 0 and 1. So if mu is 0, that means 0% of this normal force would show up as friction. If mu is 1, then that means 100% of the normal force shows up as friction. Or mu could be 0.5, and 50% of the normal force would show up as friction. Next, we need to talk about the units of mu. So what would the units of mu be? Well, if we look at this, the units of mu is actually unitless. And the reason why is because the units of the friction force are newtons, and the units of normal force are newtons. So we already have newtons equals newtons, and if you think of like as a percentage, it's just telling how much of that normal force. And there's not any units with that. We already have nice balanced units. And lastly, the value of mu depends on both surfaces. So when we look down at that roughness between there, both surfaces are important in contributing to how much percentage of that normal force will show up as friction force. All right, and there's two types of friction. We have kinetic friction, and that's if the surfaces are moving. And we have static friction, and that's if the surfaces are not moving. And with static, you can think of like static stretching, where you just reach down, touch your toes, you're not moving. You might have done that in some of your phys ed classes or practices. So static, not moving. But the one thing I do want to change here is this moving, not moving. And let's make that sliding. So kinetic friction is if the surfaces are sliding, like if we have a box sliding along the ground. And then for static friction, again, I want to say the surfaces are not sliding. And the reason why I want to do that is because moving can be confusing, because if you're running, sure, you as a person are moving along, but if we look at the surfaces, your foot grips the ground and isn't sliding, it's not moving there, so it would be static friction even though you are moving. So that's why I like to replace the word moving with sliding. the direction of the friction force is opposite the slide. So if a box is sliding forward, that friction force is backward. With a static friction, though, if you're running, what's happening is you're trying to push your foot backward, so the static friction is going to be forward in a case like that. Static friction also is how much if you need to get something started. So I like to think of that ST blend. So static is if we need to get it started, or if it's stuck, we use the value of static friction. So let's look at an example. Let's see what this looks like. So let's say that you have a box and you're going to be pushing on this box. You want to make it go. And the surface down is rough. Maybe I draw like a little dog. Some ears, because it's rough. So we want to know how much force of kinetic friction. So what I'm going to do with that is I'm going to do force kinetic is coefficient of kinetic friction times the normal force, because there's two different types of friction force and they have two different values. The kinetic friction force is the value for when it's sliding, and the static friction force is the value when it's not moving or when those surfaces are stuck together or gripping real. So the kinetic friction force, let's say in this example, is 0.4 and the static friction is 0.6. Static friction will always be greater than kinetic friction because it's harder to get it started than to keep going. So remember, this 0.4 means that 40% of the normal force will show up as friction force. And this 0.6 means that 60% of the normal force will show up as friction force. So as I solve this, if I want to know the kinetic friction force, the value of that, I put in the value of my kinetic friction, which is that 0.4, that 40%. Normal force. I need to know what the normal force is. Well, how do I get that? Well, I have to actually go back to my free body diagram, and I know I have normal, I have gravity, there's an applied force, and there's friction now. It's sliding or trying to slide, so I have friction. So the normal force is in the y, so I do sum of the forces in the y is mass times acceleration in the y. I have normals all in the y, applied is not in the y, friction's not in the y, gravity is down, so I do minus g, and this box is sliding nice and flat along that way. Nothing's happening in the up and down direction, so the acceleration in the y is 0. Or my normal force equals my gravity force, and the gravity force is little m, little g. So I can bring that over into here. And I have mg. So let's say the mass of this box is 20 kilograms. So now I have my kinetic friction force is 0.4, that 40%, my static coefficient of friction, times my mass of 20, times my g of 9.8, which is pretty close to 10. So I can do the calculations for this and find out that the kinetic friction force on this box as it slides is going to be 80 newtons. One thing to think about here is this normal equals gravity. Don't get caught thinking that's always going to happen. That only happens if normal and gravity match up and work well. If we have a cart on a ramp, we have gravity and normal, but they don't line up, so normal is not going to be equal to gravity. Or if you have a box that's being pulled, you now also have tension in the y direction. So in those cases, normal will not be equal to gravity. So don't always think that we're going to be able to do this. You've got to really look at your forces in the y direction to make sure. So now let's look at an example of static friction. So instead of mu sub k, we're going to use mu sub s and get the static friction. Now in this case, remember, it's 60% of our normal force as we go through. And if you remember, in the normal force in this example, because everything was balanced in the y, was equal to mg. So the normal force is 20 times 10, or the normal force is 200 newtons. So the static friction force is 0.6 times our 200 newtons of normal force. So the static friction force is 120 newtons. So what we're going to do is we're going to look at this, though, and we're going to look at what my applied force is and what the static, and actually not the static friction force, we're going to look at what the friction force is overall compared to what my applied force is. And if I push with 5 newtons this way, the box is not moving because it takes 120 newtons to get it moving. Think of get static started. So the friction force is going to push back. But if the friction force is 120 newtons, the friction force is going to win, and the whole box is going to slide that way. But that's not what happens. Friction is very modest. So the friction force isn't going to push with 120 newtons. The friction force is only going to push back with 5. Let's say that I get up to 100 newtons. Again, friction's like, that's cool. I'll push back with 100. Let's say I go 120. Friction says, that's cool. I'll push with 120. But once I get over this 120 newtons, let's say I get to 121. Well, the limit of the static friction force was 120. So what happens at that point is that the box begins to move because I have overcome friction. I've won that tug-of-war battle. Well, when the box moves, it drops back to this kinetic friction, which, remember from the previous example, was 80 newtons. So once I get to 121, the friction force drops down to 80. Then I could drop back to 100 newtons, and the friction force stays at 80. If I get to 70 newtons, what would the friction force be? Well, the friction force would still be 80 newtons. It's just now friction is winning, and the box is going to slow down. Eventually, the box will slow down and stop, and then at that point, the friction force will switch over to 70 newtons, nice and balanced, keeping the box stationary. Then if I try to push on it again, I could push 90. The friction force will adjust to 90 to keep it in place. So to summarize, the friction force equals mu times the normal force. And I like to say this is the fun equation. And when we look at this, we can go through and solve, and we could have kinetic friction, which is when the surfaces are sliding. We could have static friction, where they're not sliding. And remember that mu gives us the percentage of the normal force that shows up as frictional force.